One of the reasons for studying combinatorial species is that they make the understanding of exponential generating functions really very simple and intuitive. So let me introduce the generating function or generating series of a species. Firstly, we need to note that if f is a species of structures and u and v are finite sets, and sigma from u to v is a bijection, then f of sigma is also a bijection because sigma inverse from v to u exists because sigma is a bijection, satisfies the condition that f of that sigma composed with sigma inverse is the identity map of V, and sigma inverse composed with sigma is the identity map of U. Now remember that these species are supposed to satisfy two axioms. One is that they respect composition of maps, and the other is that they respect identities. And using those two properties, what we see is that f of sigma inverse circle f of sigma, well, that's going to be f of sigma inverse circle sigma, which is going to be f of identity of u, which should be the identity map of f of u. And similarly, you can show that f of sigma circle f of sigma inverse is the identity map of f of v. And so what that means is f of sigma has an inverse, and so it's the bijection from f of u to f of v. And so the upshot of all this is that if u and v have the same cardinality, then of course there's a bijection from u to v. So if cardinality of u is equal to cardinality of v, then cardinality of f of u is equal to the cardinality of f of v. And so if we are interested in the cardinalities in the number of f structures on a set, it's enough to consider just f of n, the set of integers 1 to n. And what we'll do is we will define little f of n to be just the cardinality of f of n, and we will define the generating series of the species f to be sum n greater than or equal to 0, or maybe I could say n in non-negative integers, f of n x to the n by n factorial. And this here is called the generating series of the species f. This kind of a generating function with an n factorial in the denominator, it's called an exponential generating function, and this is particularly well suited to the theory of species, as we shall soon see. So let's look at some examples of the generating series. So remember, we had the species L. L of u is the set of all linear orders on U. So L is the species of linear orders, and so a linear order on U is just a way of when you have a linear order on U, you can just arrange all the elements of U in increasing order, and you get an arrangement of U. And if you change the linear order, you change these arrangements. And so if U has n elements, then there are n possible different linear orders, n factorial possible linear orders on n. Okay, so basically what you can do is n is the set 1 to n. Every linear order is of the form sigma 1 is less than sigma 2 is less than sigma n for some sigma in Sn. And so cardinality of Ln is n factorial, and therefore L of x is equal to summation n in n factorial x to the power n by n factorial. But these just cancel, and so what you get is 1 over 1 minus x. Let's look at SU, the permutations on U, the species of permutations. So now again we know that S of n, the number of permutations of a set with n elements, is n factorial, and so we also get S of x is the same, 1 over 1 minus x. However, later on we shall see that even though the species L and U have the same generating series, they are quite different as species, and there are more subtle differences between them. Okay, an interesting generating series is C, the species of cycles. So cycle structures on you. So if you have to put a cycle structure on the set 1 to n, then it would be of the form something like x1, x2, x3, and so on, xn. But one of these elements has to be 1. So without loss of generality, we can take maybe xn to be 1. So this is x1. We can take xn to be 1. And then what we see is that x1, x2 up to xn minus 1 can be any permutation of the elements 1 to n minus 1. And different permutations will give us different cycles. So the number of cycle structures on n is n minus 1 factorial. And so the generating series here is going to be C of x is equal to summation n in n minus 1 factorial x to the power n over n factorial. But that is nothing but summation n in n x to the n by n, which is log of 1 over 1 minus x. Now let's look at dx, which is the species of du, maybe, all directed graph structures on U. Then the number of directed graph structures on U is just, so we just know what this is, because for each pair of nodes in U, you need to decide whether or not there is a directed edge for every ordered pair. So dn is just going to be 2 to the power n squared, if you allow loops also. So for every pair belongs to n squared, you need to decide if there is an edge. And so you'll get dn dx is equal to summation n in n 2 to the power n squared x to the n by n factorial. I do not know of a nice way to write this. Similarly, gx. So in this case, we have a nice formula for the cardinality of dn, but the generating series is not some very nice function that we know of. Gx, Gu is graph structures on U, simple graph structures on U. And again, now if we do not assume, so they are not directed, and if we assume that there are no loops, then basically we have n choose g of n, we have n choose two unordered pairs of elements in 1 to n, and for each of them we have to decide whether to put an edge or not. So it's 2 to the power n choose 2, and so g of x is equal to summation n in n 2 to the power n choose 2 x to the power n by n factorial. Okay, so these two don't really have very nice functions associated to them, whereas these s of x, l of x, and c of x actually have nice functions associated to them. Let's look at another one which has which is quite simple but has nice functions associated to them. P of u is the subsets of u, or the power set of u. And so we know that P of n has cardinality 2 to the power n, and so P of x is summation n in n 2 to the power n x to the power n by n factorial, which is just e to the power 2x. Now let's look at some of the species that we had defined by what I call direct definition. So there's the species epsilon, which is just the species of elements. So this was defined as epsilon of u is just equal to u for all finite sets u. And so epsilon of n here is just going to be n. And so the generating function epsilon of x, the generating series, is going to be summation n in n, n x to the power n by n factorial, which is just n in n x to the power n by n minus 1 factorial. That's just, you'll recognize as x e to the power x. Okay, recall the species x, the species of singletons. And what we defined is that x of u is equal to u if cardinality of u is 1 and the empty set otherwise. So x of n is just going to be 1 if n is 1 and 0 otherwise. And this explains, now you see the generating function of x is just x, which kind of explains the notation capital X used for this species. Then there's the species 1, which was defined as the species 1 of u is equal to so this is called the empty set. So 1 of u is u if u is the empty set and it is empty otherwise. And here you see that 1 of x, okay, so 1 of n, cardinality of 1 of n is 1 if n equals 0, that's the only case when this is the empty set, and 0 otherwise. And so the generating function of this is just 1, again justifying the name for this empty set species to be called 1. And then we had the species E, the species of sets. E stands for ensemble, the French word for sets. And here you recall the definition was E of u is just u, the set u viewed as it's a singleton. And the generating function for this is therefore just summation n in n, x to the n by n factorial, which is just e to the power x. Let's see. Okay, maybe one more. Ek is the species of sets of cardinality k or size k. It's defined as EKU is equal to just the singleton set U if cardinality of U is k and empty set otherwise. And what you see is that Ek of x, well, Ek of n is going to be 1 if k is equal to n, and it's going to be 0 otherwise. And so the generating function Ek of x, the generating series, is just x to the k by k factorial. And finally, we have the empty species. I think maybe I called it 0. 0 of u is the empty set for all u. Then, of course, the generating function of 0 should just be identically 0 because all the terms in the series are 0. Now, there's some series for which it's not so obvious what the generating series is. For example, the species of set partitions. So there it turns out that the generating function has a very beautiful expression. It's just e to the power x minus 1. And we will see how to derive this very conceptually as we develop the theory of species. Other such interesting generating functions are those for involutions, rooted trees, etc. And those will become easier as we learn more about combinatorial species.